I think we can go ahead and start right on time.
Okay.
Next speaker is Dr. Alisia Fadini. We're going to hear from her about, I think, how to trick AlphaFold into doing X-ray structure refinement.
That is a good way of putting it. Let me see if I can. Do you guys see this?
Yeah.
Yeah. Okay. Great. Yeah. Okay. Then oops. I guess I'll get going. I was hoping. Yes. Okay. Yeah. Great. So thanks a lot for having me. I'm kind of sad not to be able to be there in person, but I'll kind of Kevin just introduced, I'll kind of be talking something very similarly to what we just heard about, but how we can use OpenFold, which is the open source implementation of AlphaFold 2, as a prior for guiding structure prediction in kind of atomic model building for crystallography and some maybe hints of cryo-EM. And we're doing this with a little program that we've called Rocket for now. So before this goes kind of and gets lost at the end, I really want to say this has grown from last year into a pretty great collaboration. So I'm based in Cambridge with Randy Reed's group and at Columbia with Mohammed Al-Qurashi. And I've been working very, very closely with Minhuan, who is here and is recently graduating from Duke Hextras group at Harvard. So a lot of the work I'm showing here is Minhuan's work too. We've had a lot of support from the Phoenix collaboration and the OpenFold teams. So just want to acknowledge everyone else that's making this possible. And the problem we're looking at is really the issue of modeling protein structure to X-ray crystallography data, and in particular, the model refinement and rebuilding. So I think some of the audience here in this room already knows that model building can be difficult and time consuming. It can really depend on when you're trying to model into electron density, whether it's from cryo-EM or crystallography, it can really depend on the expertise of the person who's trying to do the refinement, and things get really messy if you have low resolution or disorder. And so what the people from the Phoenix collaboration, but kind of more or less everyone in the field has noticed is that using AlphaFold 2 models, and this is also valid for AlphaFold 3 models, though I'm not really going to go into too much detail on AlphaFold 3 today. But these AlphaFold models, they're really great starting hypotheses to essentially take the prediction and initially fit it into your data and then do this final rebuilding and refinement so that you get a model that's actually maximizing the fit to the data. But this extra step of having to collect the data and doing the extra rebuilding and refinement is actually still very crucial, because the models that we get out of AlphaFold in terms of really nailing down the details that we are interested in for understanding protein chemistry, or how proteins might change their interaction to another protein or a ligand, or their susceptibility to the environment, we're still pretty behind in terms of predicting that without any sort of experimental aid. And then there's also the problem that I think it's maybe less appreciated than in other fields like NMR, but also in crystal structures, we have an ensemble of states in the crystal that is we often observe in the form of alternate conformations. And so right now we have the problem that AlphaFold 2 models don't really have. They still only propose a single structure. So there's no way to model this, and you have to go in and do it by hand. And so we've gotten really good at collecting a lot of X-ray crystallography data, and this refinement and rebuilding step really remains the bottleneck. So I think these are, to give an idea, some statistics I collected since January 2023. There were around 15,000 PDBs that were deposited by crystallography in the PDB data bank. And I think most people agree that even with a very conservative estimate of 10 hours per structure, that's still 150,000 scientist hours that went into the refinement of these structures. And we hear a lot about kind of large scale fragment screening. We've seen it already start with some kind of projects that were launched during the COVID pandemic, and some beamlines, I was recently attending a talk where like the diamond synchrotron is thinking of going up to 10,000 crystal structures per day at a certain point. So we're going to want to really up our game in terms of how easily we can automate this refinement and rebuilding. And it's not really just about drug discovery. So I think CAR-EM is already onto this a little bit, but there's this interesting observation that by collecting a large number of snapshots of protein structural data, whether they're just a large statistical sample or there's some time resolved trajectory, you might actually start to study the structural variability and understand some functional dynamics that are maybe represented by the variability between structures. And so for kind of these scientific cases, it's really important that we work on the automation and the speed of the refinement and rebuilding in crystallography. And so I have here just a point I want to make. I think it's also not just about automation, but it's also there's something to be said that the models we are using right now, and maybe it ties into what Kevin introduced at the beginning, they might not be completely adequate for explaining our data. So in crystallography in particular, we have this observation where our overfitting metrics are really much higher than we would expect. And here I'm just citing kind of two interesting reviews that start analyzing and ascribe this problem maybe to the fact that the macromolecule model we use right now is not really representing protein flexibility and protein solvent interface as optimally as we might maybe want. So I think there's also an interesting opening here for using machine learning algorithms to maybe provide us with improved prior distributions that could help us address this overfitting problem as well. So our big picture question is, can we automate a robust and accurate way of going from an X-ray diffraction data set to start to a single or hopefully multiple, an ensemble of protein structures, helping ourselves with better priors from machine learning algorithms? And so here on the right, I just have an example of one of our refinement trajectories for an able kinase that it's kind of a sneak peek into the results I'm going to show later, but I just want to show how the pink initial alpha prediction refines itself to this transparent density during our refinement process. And I wanted to put it here just to say that kind of next to this big question that I think we might not actually be so far from being able to automate this process, even when it involves some large conformational changes that need to happen. So our core idea was, let's use maybe some stronger prior from machine learning, and AlphaFold we've observed is a very good initial prior, and we've used it manually as the starting model for a lot of refinements. So our concept was, can we somehow inject information from the diffraction pattern into the AlphaFold prediction process so that we can guide it towards a structure that will maximally fit our data? And so the question is obviously, how might you go about doing this? I think there's probably most people here are quite familiar, but just as a quick reminder of the OpenFold AlphaFold 2 framework, there's kind of these three main information streams that come into the network. There's the multiple sequence alignments of coevolutionary information, the sequence of the structure you're actually interested in, and then some maybe homolog template that you might feed to help the prediction process. And these are embedded into some initial representations, and then they go through EvoFormer and the structure module to eventually output the protein structure for the sequence that was provided. And so when we were kind of at the drawing board about a year ago, and we were trying to think of where we might want to insert some experimental feedback or information, we really were looking at either the inputs or the initial embeddings. And our rationale behind this was that this would in some way let us modify the prediction process while still making the most, without any further retraining, making the most of the weights that were learned during AlphaFold training kind of downstream. without also changing any sort of coupling within evoformer. And we weren't the only ones who thought about this. I think Hannah was also in the room earlier, but there were quite a few preprints and papers that came out that were looking at how you might inject information or tweak either the inputs or the initial embeddings within AlphaFold to like trick it to like access different conformations. And our idea was to try as a first step to implement what I've called here an iterative search-based refinement. So how this works is essentially you take the vanilla open folder or AlphaFold 2 and you do a single forward pass. And this provides you with a model. Now, if you have your experimental data, so our crystallography diffraction pattern in our case, and you have some way of formulating a maximum likelihood target, so the probability of your data given this model, you have a way to compute a loss of what this model is compared to the data that you've collected. And if you do this differentiably, you can then essentially do backpropagation and a gradient update to some embedding upstream of the prediction process and ask the model to modify its prediction so that it minimizes your loss. And you can do this iteratively and eventually, hopefully, converge to a loss that's minimized. So this is what the big picture process that we wanted to implement. We needed to connect OpenFold to our data target function in a way that was fully differentiable. And that's where Minhuan's kind of graduate work really became essential in getting this up and running. And then once you have this, then you can compute the likelihood with respect to the atomic coordinates that were predicted by the network and any current iteration, and you can start iterating through and updating. So we're doing this gradient-based search for an embedding that will lead to a set of coordinates that maximize the fit to our data. So I've kind of left this purposely vague right now, but obviously our big question was maybe which embedding should we go and try to modify, which will be the most effective. In terms of embedding choice, we really focused on these three initial representations. So the first features that come into AlphaFold before evoformer, and we were looking for. We wanted to be able to move in a space that would maintain viable protein folds and geometry, while at the same time really maximizing the diversity of structures that we would have access to during our search. And so we actually started by doing some small tests in each of these different embeddings and seeing how far what type of structures we were able to access. And this is just a very qualitative result of that we've been able to reproduce on a few systems, but this is again the able kinase I was showing earlier here. So we're looking for the space that gives us access to the largest amount of conformations. And we saw consistently that moving into the MSA representation was the most effective from this perspective compared to moving into the template torsion angle space or the pair representation. So we decided to kind of focus on the MSA representation based on these small tests, and we have implemented this iterative search-based refinement, and that's what we're calling Rocket right now. So this is what Rocket is. It's a biasing of the MSA representation feature in an iterative fashion so that we minimize the loss to and maximize the likelihood of our data given the model that we have. So we're learning these kind of weights and bias tensors that will let us perturb the initial MSA representation. So this is what we started implementing, and we wanted to test it on the simplest case possible at first, just to see whether it worked at all as a concept. So I'm showing here our first test case, which is just a very high resolution lysozyme structure, not particularly exciting. So I'm showing the initial AlphaFold model prediction in light blue, and then I'm actually going to do this throughout the presentation, but I'll show either the density or the model that we've verified is a very good fit to the density and was deposited in this transparent outline. So you can see that this backbone doesn't need that much refinement, except for maybe some mild adjustment of this domain up here. But I wanted to pick something that was quite easy in terms of backbone rearrangements, because I thought it was quite important to try to assess whether with this little method that biases the MSA representation, we could actually access different rotamers and different sidechain conformations, which at the end of the day is a level of detail that we really want when we do our refinements. So before I show the results, there is kind of an important factor that I will just need to mention, which is that normally on top of coordinates in crystallography, and you would refine these B factors, which are essentially accounting for how smeared the density is in that particular area of in that particular region of the protein. It might be caused by disorder, partial occupancy, or flexibility. So usually this is refined together with the coordinates. In our case, we're using a pretty common yet empirical formula that converts the PLDT confidence from AlphaFold into a pseudo B factor. And so I just wanted to show it a little bit here intuitively. What we're seeing is kind of that anything above PLDT of 70 is still a pseudo B factor of around 100 or less. And then as that confidence decreases and becomes less than around 60, we have this kind of exponential increase in what the pseudo B is. And so right now, rather than refining the B factors, we've simplified our job a little bit, and we let the B's change with model confidence as the model confidence changes over the refinement, but we don't actively refine the B. So that's an important point in terms of what we're doing, and it will become a little bit more important later as well. So this is the trajectory there. I'm going to play in just a second. I'm not showing any morphing because I really want to show what the optimizer is doing at every step. So we start, and maybe you can kind of just see this upper domain. It quickly kind of like snaps into place. Nothing particularly exciting needed to happen, but we can kind of track essentially the correlation between the map that we can calculate from the model and the map that we can calculate given the experimental observables. And so you see before and after rocket, we still see a considerable improvement. This is this domain that kind of snapped into place and is getting better. So this improvement is, there's not much happening on the backbone level. So my question was, what's going on with the side chains? And interestingly, and excitingly for us, we actually saw that just biasing the MSA achieves a pretty good side chain fitting into experimental density. So I'm just going to play these videos now. In the cases of the 2 phenylalanines where the density is pretty good, this immediately snaps into place and then slowly readjusts itself so that it's kind of actually centered within density. And then here I have the case of a glutamate where the density is much less clear. And here you can see that the model is kind of sampling different rotamers, and eventually it converges to a rotamer that's quite different from the one that the depositors chose in gray, but I would argue probably just as good in this case. So from this first test, it was kind of a proof of principle to show that we could refine simple backbone rearrangements in a simple case by using rocket. But it was also important for us to kind of confirm that we could achieve the level of detail of sidechain fitting into experimental density just by this process of biasing the MSA. So I kind of felt ready for a harder case that I'm going to show. And this is the Abel kinase examples I've already kind of sneak peeked a couple times. And so this is the human Abel kinase is an important therapeutic target. And compared to the initial AlphaFold prediction, we are looking here at an experimental structure that actually needs to have quite a few large conformational changes happen. So this glycine loops needs to be remodeled over to the side, and there's a bad density region and a helix that needs to kind of translate into place. But importantly, the DFG loop, which is this loop that's quite important, that's essential for determining whether the protein is active or not in terms of its conformation, in this case is predicted in the opposite conformation compared to the experimental density, which is over on this side. And these loops, also because they're present in the PDB in different conformations and because they're large loops, they're actually predicted with low confidence by AlphaFold, which is why often other automated refinement protocols will chop them off and leave the user to have to somehow try to rebuild them. So how does Rocket handle this? So I'm going to play the trajectory here. You can keep an eye out on this loop, on these two loops. So in our case, this loop actually pretty quickly snaps into place, and then there's some readjustments that needs to happen in the lower section. So we kind of have to use a higher learning rate to be able to access these larger conformational changes. But you can see that we quickly, maybe I'll play this again. We quickly, after some sampling, we adjust into a conformation that is a very good fit to the density and is also pretty high confidence throughout. And so here I'm just showing again, residue by residue, the correlation between the map we can calculate from the model and the map that we obtain experimentally, and the difference between just the AlphaFold model and then the model that we've refined. Here we can add, Phoenix Refine is a more standard crystallography refinement technique that we just concatenate at the end, again, fully automatically, so that we can add some waters and refine B factors. And so if we string these two processes together, we can get something that's very close to what the depositors ended up depositing into the PDB. And so there seems to be an interesting point here, is that there seems to be this tracking of the model confidence and the fit to the data. And I think it's particularly noticeable in the case of this loop that I've zoomed into. So I'm going to play kind of on the left the example where we do some sampling, eventually we converge onto a loop that has a pretty good fit to the density, actually. And this is reflected by some high confidence for the residues in that region. And then on the right here, now I'm playing an earlier refinement where we had some suboptimal parameters. And in this case, the loop never converges to something that's within density, but it kind of remains low confidence and seems to self-report for this fact. So this is an important, I think, an interesting observation that I'm happy to maybe discuss more about if people are interested in later. But what we can say that we can do is we can automatically go from the initial AlphaFold prediction to this pipeline that uses Rocket, and then more traditional, like a small, like a few cycles of more traditional refinement, and rebuilds most of the backbone and side chains into density. And in crystallography, we look at this R factor, so the agreement between the observed structure factors or intensity of the diffraction patterns and the ones we can calculate from the model, and the lower is obviously better. And in our case, we get R factors that are actually slightly better than what the depositors put into the PDB, and comparable to this PDB redo bit database, which is supposed to be the state of the art that has somehow gone through multiple deposited PDBs and tried to optimize them. And right now this runs on 1 to 2 hours on an A100 GPU with 40 gigs of memory. We haven't tried to optimize this at all, so it's kind of the stupidest implementation memory-wise that we really want to eventually start working on a little bit more. But what we've learned from these tests up to now is that modifying the MSA embeddings seem to be the most appropriate in AlphaFold 2 for accessing large conformational changes, at least based on our tests, while at the same time allowing us for the detail of refining different sidechain rotamers and mobility. And we were quite happy to see that this idea of doing an iterative search strategy can guide structure prediction towards something that automatically then matches the experimental crystallographic density. Now, what we wanted to see in terms of the immediate next steps was we wanted to make sure that this could actually generalize to a diverse set of folds. And what we've done is essentially take a data set of 102 X-ray structures that were difficult molecular replacement solutions. So essentially what that means is that they are a very diverse set, and they lack homologs in the PDB. And these in particular were all released after the AlphaFold 2 training cutoff. So we're kind of doing this in the hope to avoid any sort of leakage there with the structures that we're able to reproduce. And approximately 30 of these cases are a single chain in the asymmetric unit, which essentially just means that we don't need to model any type of protein-protein interaction or two proteins at a time. So that's what we're handling right now. And so we ran Rocket on these 30 cases. And here I'm showing, again, these R factors that are basically either we just take the AlphaFold model and add some waters and refine just like the B factors, but keep the atomic coordinates fixed. Or we do our automated Rocket and Phoenix refine pipeline. And what we see is that we always improve by more than, in most cases, more than 7% in terms of the R factors before and after Rocket. And so here, I'm highlighting and coloring each structure, which is a dot in this plot, by what I've called here model completeness, which is essentially how many residues at the end of refinement have a confidence higher than 70 in terms of PLDVT. And so there are a couple cases where I've highlighted here that we actually still have some residues that are low in confidence. And it's kind of interesting to just see when that happens. So in some cases, so I'll play the refinement trajectory here on the left. In some cases, we have no density in some loops. So you can see this helix is, compared to the beginning, slowly falling into place. But the two regions where there's no density, our model tries to sample different loop conformations and eventually just settles on something with low confidence. And that's actually good for us because it is a way of reporting that we've come up with some coordinates, but we have no experimental support for this. And in another case, this on the right, sorry, here is a case where we're refining a lot of the details in the rest of the backbone. But for example, we have a high energy peptide flip that needs to happen here, where the density is good, but our initial model is quite different, and this flip doesn't happen. And here again, we're reporting the model reports some low confidence, and it's correct in doing so because it hasn't achieved a good fit to the data. But this is not a perfect scale yet. So I think I've highlighted here on this other model a little loop where the AlphaFold is still highly confident of this conformation, even though we have no experimental density for these residues, and a peptide flip needs to happen to put us into density. So I think what we're learning a little bit from this is that the simplistic empirical formula we're using to convert B factors to pseudo Bs is to convert confidence to pseudo Bs is definitely a point we want to work on. And so the other thing we want to work on is we are really curious to know if this can really help modeling at low resolution, and we believe it should because the geometric prior that comes from AlphaFold is really strong, and this is the data set we're working on right now, but the results are still a little too preliminary to share today. And still in the kind of theme of low resolution, we thought this would be also a really good case for looking at cryo-EM model building. And so we formulated the same concept of the rocket that I've just explained, but substituting the crystallography target with a cryo-EM likelihood target, where we treat essentially errors in different directions in reciprocal space. And so this is just a prototype for now, but cryo rocket, we're hoping to see if it can be useful the same way that it can be useful for X-ray crystallography, and we'll be looking for test cases or new data sets in the next couple months in case anyone has some interesting data that they'd want to share. And then there's another kind of implementation detail we'd like to work on, which is, it's pretty simple theoretically, which is to substitute our vanilla AlphaFold or OpenFold that we're using right now with a multimer version. So that would let us essentially model multiple structures at the same time. So if you have multiple chains in the asymmetric unit, you could model those together, and we wouldn't be constricted in the systems that we want to look at. So these are all what's coming next, hopefully in the semi-near future, and mostly implementation details. What the ambition is for this type of project, I think it would be really exciting to see us refine a large fragment screening data set automatically. And this involves obviously also having some protein ligand co-folding refinement, but the likelihood target from the crystallographic side can deliver if the machine learning framework exists. And this is what we're working with in Mohammed's group. And we'd also really like to, rather than do this iterative procedure, which is a little bit more time consuming than a single shot inference, we'd like to build towards a single shot inference model where you would have a data set and a sequence, and you would get a structure that maximizes the fit to the both data and sequence out. And I think we're better placed now to maybe start understanding how we would go about building this network. And similarly to the protein ligand co-folding, I think it would be really exciting to extend this approach to fitting ensembles. So if generative models exist that let us plug in crystallographic or cryo-EM likelihood targets, this becomes a really interesting application. And so I think I'm more or less on time, so I'll stop here. And if anyone has questions or ideas, I will be happy to answer or talk. Yes.
Hi, thanks for a very nice talk. I have a question that I'm not sure makes sense, but I'll ask it anyway. Do you think would it be beneficial to also think about modifying the standard statistical modeling framework that X-ray structure refinement follows, the traditional X-ray structure refinement follows, with AlphaFold considerations, in contrast to what seems you did, which is you modified the AlphaFold machine learning framework by incorporating X-ray considerations. Like the goal is the same, is bridge the gap between the two or keep the best of both worlds, so to speak. So why did you start from one side and not the other?
Yeah, I guess it's a bit of a circular problem. Like it kind of depends how you frame it. But what we've done here is we've kept kind of our Bayesian and likelihood formulation of the crystallographic likelihood target, and what essentially we're doing is we're using the AlphaFold forward pass as our prior. I think the reason we decided to start from that is the natural extension of what people were already seeing more manually, which was that if you start from a AlphaFold model, we have really good ways of kind of modeling the errors in our experimental data to try to account for this and reduce overfitting when we're actually refining the structure. And that is very powerful. So these likelihood targets that Randy was instrumental in developing over the years were not straightforward, and we've seen in the past that it can, even just moving from a least squares refinement target to a maximum likelihood target can make a big difference in the quality of the model. And so in our case, it was kind of natural to try to mess with that last, but it's not necessarily I don't think it's necessarily a bad idea to go there eventually. I think for the single structures, maybe it doesn't make that much sense yet, but when we want to go and refine ensembles, then I think we'll have to start maybe thinking about reformulating the data model side of things a little bit more. So how to do that, though, is not completely obvious to me right now. You need to be careful when you're trying to fit an ensemble to a crystallographic data set in terms of the ratio of parameters to observations that you have. So it's not a straightforward problem, but it's a good point. Yeah.
Thank you.
The questions?
Yes, hello. Thank you for the great presentation. And I was wondering if you had an idea about what really enables the model to snap into place in the regions where you have a large deviation initially. Essentially, I'm wondering if this comes from the fact that a slight modification in the weight will trigger a large deviation on the output, or if you're using some sort of trick on the expression of the likelihood, if there is some sort of coarse to fine approach there.
So we have to develop a kind of more aggressive strategy in terms of refining these larger changes. How our refinement method protocol works right now is that we kind of have a high learning rate stage at the beginning that is not doing a completely random sampling because it's still a gradient descent based on the likelihood, but it allows for these larger changes. So I don't know if you saw, but there were these intermediate structures that were pretty low confidence. That was quite important in terms of actually being able to sample the larger changes. So that's what we do right now. We have this essentially larger learning rate is what lets us take these kind of slightly larger steps that kind of knock us out of local minima slightly, and then the target function is still able to slowly descend into the correct place. And so we actually don't need to adjust the learning rate, we don't need to schedule the learning rate ourselves. The Atom Optimizer does a pretty good job of taking smaller steps once we're closer to a minimum, but that was definitely a big part of developing kind of the right way to sample larger changes as well. Yeah.
Hi, Alisia, this is super interesting. Really enjoyed hearing about this. I'm curious about the bias that you're learning on top of the MSA, and if you've had the chance, do you think that it's just sort of enough of a random perturbation, or do you think are there interesting sequence things that get learned in the bias, for
yeah yeah? So I mean, obviously this was a very interesting question for us, and Minhuan and I have looked at this. It quite excitingly does seem like there is information in terms of the sequence changes that they're not random. But we are trying to kind of divide the two problems for now. So we've left this on the back burner temporarily in terms of, it's different problem. One problem is looking at the crystallography data and trying to fit a new model. And one thing is, can you perturb biases maybe on any loss really? And can you start learning from these new biases in terms of the mutations that you might extract from that. And so the answer is, it seems from our preliminary results that the answer is yes. But how to do that is not completely obvious. So we're hoping that the data is noisy, right? There's some signal there, and then there's a lot of noise that comes from just our gradient descent. So we're working on how we could extract that mutation signal while getting rid of all the random junk that's also getting accumulated. But it's a really good point, and we're very excited about it. So we're very much interested in looking at all these biases statistically.
I think, Tom, you had your hand up last go around.
That was really very interesting. Thank you. So my question is more about the computational resources required to sort of train this. Are you doing some kind of fine tuning or something, or did you train this from scratch? And where are you getting these kind of resources to do this?
Yeah, no, I mean, so originally we were thinking that we might consider retraining or fine tuning the network so that we would kind of just have something that is, so this goes maybe to my last point here. If we wanted to go more towards a single shot inference approach, then we really envisioned that we would have to retrain the network on both models and data sets. But actually at the moment we are not, we're using the AlphaFold parameters as they are. So we're not doing any sort of retraining of the network. And what we're learning in our gradient descent is just a perturbation to this inner representation. And so it's still not cheap to do, because we're doing this kind of iterative for, a refinement is essentially a refinement done on a GPU. So you have to do this back propagation through the OpenFold network, and that's what takes resources. And right now we're still working kind of on the proof of principle. That's, I think I mentioned this towards the middle of my talk, but we haven't tried to optimize this very much. But this is where in the lab we have a lot of expertise in terms of, for other reasons, they're working hard to try and minimize the cost of doing the back propagation for large chains. So we'll just kind of incorporate anything that comes along into this. But I think eventually we want to do like a single shot inference, and that would require retraining, but that needs to be done once, right? And then once that model is trained, like anyone can use it without any form of, without needing to retrain themselves. It would be a general network. If that answers the question?
Yes, thank you.
Great talk, Fika. A couple of questions. So one, did you see any repeating structural patterns of sort of things that AlphaFold, on the first kind of fold iterations you were able to get really well, or were like repeatedly fixing really well into density? And then second question is sort of on thinking about ensembles and alternative conformations is, did you have any structures in your data set in which there was very obvious sort of 50-50 side chain density, and how did the model go about sort of choosing which position to be in?
Yeah, okay, so answer to the first question, it's not so much, I think it's actually less about AlphaFold here and more about the likelihood target. So kind of the how strong the gradients that are coming from the likelihood target are. So we've actually noticed that if there is some form of like smooth, like rigid body motion that needs to happen, or a helix that's at the wrong angle, the gradients from the likelihood target are strong enough that they can kind of guide the model towards that. Whereas cases where higher energy cases where you need a flip of a peptide backbone, or you need to completely remodel. So it's, for example, if you need, we looked at a couple cases where the fold needs to change significantly. And there, the problem is that you are kind of reliant on the stochasticity of the gradient descent to kind of land in the right place and get positive feedback from the likelihood target, because there is no signal in terms of the gradients from the likelihood target. So that's really what limits us in terms of what we can do or what we can't, is the type of gradients that we can get. And this is where I think the first question of should we maybe rethink also the type of target we're using is very relevant. And the second question is, yes, so we had a few cases, you know, it's often the case in these structures that solvent-exposed residues are kind of flexible and can toggle between two cases. In this case, it's similar to what I showed with that glutamate. Like, we see the model kind of like sampling around, and it clearly just doesn't have strong signal in either rotamer, and eventually it picks one that's fine, right? But our current the current implementation of AlphaFold will only ever have one residue, and we haven't tried to like add, you know, I haven't wanted to do any sort of jigsaw mix of different conformations and trying to stick them together, because I think it's really worth, we see it even within our group. It's worth, I think, waiting for a generative model that can just generate a weighted ensemble of some form, and then try to use that in the likelihood, like with a likelihood target, rather than doing some piecewise. So for now, we're just happy with it picking some middle ground, essentially, and as long as it's still reasonable with the density.
Okay, I think it's time to move on, right? So thank you very much, Alisia.
Thank you. I'll stop sharing.